All right, you want to give us a test, a quick test? Check, check. Yes, we can hear and see you.
Okay, good. So hi everybody, can I start now?
Yeah, you're good to go.
Okay, good. So I'm Makoto, I'm connecting from Geneva in Switzerland. Yeah, actually at CERN, actually the organizer asked me to go to show the lab to you, but it's actually 11 p.m. on Friday night, so there's safety issues of me being alone in the lab, so I'm connecting from a hostel room. But I can maybe show you a parking lot. And with some snow. It's been a cold winter here as well, actually. So, Marcello gave a really excellent introduction, and he went a little bit over time, only factor 3 or so. But I thought I was going to show you first some video that CERN made to just give a little bit of a feel of what the lab looks like. And then I come on and talk a little bit about more about the experiment, and then I probably end with the animation that describes a little bit more about what we do. So in this first video, you see my friend and colleague Jeff talking about explaining the alpha experiment, and also featured in this video is the TRIUMF postdoctoral fellow Joseph, who's in long hair and beard. So why don't we start with the YouTube video, Stu?
Yeah,
please.
for sure. I'm going to switch you around so you can follow along.
Okay.
So what we've done is we've tried to shine the same color of light, if you will, on an anti-hydrogen atom that we would use for hydrogen, to see if it responds in the same way. In particular, is the frequency of that light.
Oh, actually, are you guys hearing the sound of the video?
The same exact frequency that you would use to interact with atoms of hydrogen. And the answer so far is yes. When we went looking at the place where we expect to see an effect in hydrogen, we see an effect in antihydrogen. Now, what really matters here and for the future is how precisely you do that measurement, right? So right now we have a precision of a few parts in 10 billion, right? We hope to get much, much better than that. The precision with hydrogen is a few parts in 1,000 trillion. So for me as an antimatter physicist, it'd be fair to say that this is a dream come true. This is what I set out to do more than 20 years ago, to actually look at this transition in antihydrogen. There's a lot more work to do, but I can say that this is the biggest step in my career, in the history of this type of experiment. This is what we set out to do. This is what the machine was designed to do. There's a lot more work to come, and it opens up a whole new branch of physics, if you will.
Okay, so as Jeff said, this was really a very exciting moment for us. The result we just achieved and published a month ago in Nature. And so basically what we did was to study the spectrum, the color of the antimatter atoms. And as you heard from Marcello, hydrogen atom we know very well for over 100 years. And to study hydrogen is a little bit more easier because you can buy order hydrogen on eBay or something like that. You can buy a bottle of hydrogen. But anti-hydrogen, they don't exist naturally, so we have to synthesize it artificially by combining its ingredients, which are themselves antiparticles. So the antiprotons and anti-electrons we mix together to produce anti-hydrogen atoms. Now the one big difficulty with this kind of experiment is when you have antimatter, colliding with matter, they annihilate into energy, as you heard from Marcello. So basically, there's no easy containers to contain antimatters, because as soon as it hits walls, they disappear. So we developed several years ago this device called magnetic bottle. So we use the force of magnet to suspend antimatter atoms and prevent them from hitting the walls. So we've been working with this magnetic bottle for past several years. And only recently we've been able to use laser beam to probe its structure of anti-atoms for the first time. Now, how do we see anti-atoms? I think it's a little bit philosophical what you mean by seeing something, observing something. So that's something the artist might want to think about. But we see antimatter, we observe antimatter by letting it disappear. The way we know that antimatter existed was by artificially letting antimatter hit the matter and then observing the annihilation reactions. Then you saw that okay, antimatter had existed. So practically what we do is release antimatter from this magnetic bottle, let it hit the walls, and then detect reactions from this annihilation of matter walls. So that's what we do, and I'll show you in a minute the animation of a little bit more how it's done in detail. But this was really the first step, the first time anybody was able to use laser beam to study antimatter. But the precision we achieved is already very, very astounding. So we measure the spectrum or the color of antimatter atoms to the level of a few parts per 10 billion. In this first demonstration experiment. So part per 10 billion, it's hard to imagine perhaps. So I just calculated a few minutes ago. I think when you drove or took a bus from Emily Carr University, which is in Grand Island, right, to UBC campus, it's about 10.4 kilometers according to Google. So the 1 part per billion of 10 kilometers is 1 micron. So our initial measurement is equivalent to measuring the distance between your institution and this lab, the TRIUMF lab, with accuracy of 1 micron. And 1 micron is smaller than the size of bacteria. Now, but we're just beginning, so much better known. So our goal as an antimatter physicist is to try to match hydrogen atom. And hydrogen atom is known even 100 times better than what we measured. So there's some way to go, but we just started this really exciting series of measurements now. So I'll finish with the animation of this. So this is a bit of an artist concept animation of what we do.
Can you see okay, Makoto?
Yes.
All right, you tell me when.
Okay, please go. So, oh, actually, I can't see the. Oh no, I think it's okay. So what you're gonna see is the outside of the alpha apparatus, core part of the alpha apparatus, which is you see the 3 layers of a particle detector. So these 3 layers of the detector is the device that detects annihilation of antihydrogen on the walls. And so we peel off these detectors, and then you see the inner core of the equipment. So what's shown in this copper is coils that produce this magnetic bottle. And it's actually, we send a lot of current of order of 1,000 amp into these coils. And these coils are held at a very, very cold temperature. And the device that cool all this temperature was built at TRIUMF, so-called the cryostat. and the cryostat keeps the whole apparatus at 4 Kelvin, which is about minus 270 degrees Celsius. It's very, very cold. And you send in these currents and in order to produce a trap from the magnetic bottle. Let's see. And so this, if you further, yeah, so these are currents that are being sent through the coils. Now, if you, in the next step, you will peel off these walls of an apparatus, and then see these gold stuff. These are called electrodes, and these are the device inside our apparatus to produce using electric field in order and help create synthesize antihydrogen atoms. So what you see, and the whole thing is really in so-called ultra-high vacuum. So we pump out any gases, airs that is in the apparatus. So and we mix gently this antiproton and anti-electrons in order to produce antihydrogen atoms. And typically what happens is that 2 anti-electrons collide and then in nearby of antiprotons, and then one antihydrogen is formed, the other anti-electrons moves away. So this is how we form antihydrogen by the synthesis of antiprotons and anti-electrons. So what you see is what looks like a bathtub in there is our trap. So this is our magnetic bottle. So antihydrogen atoms are trapped in this bottle. And we release atoms by shutting down this bottle, and then antihydrogen hits the walls and annihilates. And these produce high energy particles that register signals in the detector. So this is what you just saw by release of the antihydrogen atoms. You see annihilation. Now I move on to the spectroscopy part. This is the newest part of the results. So here, what we do is to send. So we pictorially trap 2 antihydrogen atoms in a trap, and we send laser beams, very intense beam of a laser light. Now, if condition is right, then you can cause a transition of this antimatter atoms, and laser light is absorbed by atoms, and then by another light you can destroy these atoms. So what happens is when condition is right, antihydrogen is destroyed. And we do these experiments by sending light. At the end, you count how many are left over. So what's missing is destroyed, has been destroyed by laser light, and what's remaining didn't react with the light. So that's how we know by destroying these atoms, either by hitting the walls, letting it hit the wall, or destroying it by interaction with the laser light, we can see antihydrogen has existed and reacted. So that's all for now, and I guess I used up my almost 15 minutes, so maybe there's time for one or two questions now, people have quick ones. Otherwise, David and Marcello can answer your questions at the end of the seminar.
Is there anyone with a quick question? All right, I think we're going to save them until the end.
Okay. Well, thank you, and enjoy the rest of your stay at Triumph.
Thanks so much, Makoto. We'll talk to you soon.
Thank you.
Bye.